Okay, so last time we stopped at, I believe we finished the full wave controlled rectifier, correct? So let's see where that is. Full wave, three-phase controlled rectifier. This is the uncontrolled. Yeah. So last time what we did was three-phase controlled rectifier. So I hope you go back and draw. Change the value of alpha, for example, and draw the output voltage, right? And try to make sure that you understand what we did. The process we followed. Hopefully it's clear in the video, and if you have any problems, please don't hesitate to get back to me. Okay, so what else? So with the three-phase controlled rectifier, like the single-phase controlled rectifier, again, I can change the value of alpha. Again, if you look at the equation for output voltage, this is the average output voltage. So they just integrated, the period here is not full cycle. You can, because this thing is being repeated, right? So the waveform that we have is repeating. So we don't need to integrate over the full period anymore. We can integrate from from 60. They integrate from 60 to 2 pi, but to 120. Yeah, from 60 to every 60 degrees. Remember, we have 6 pulse output. For the diode case, we have 1, 2, 3, 4, 5, 6 pulses in one fundamental period. This is one fundamental period, right? So since we have 6 pulses in one whole fundamental period, for me to calculate the average output voltage, I can calculate it over the full period. You can do that. And in that case, you have to take every 60 degrees, you find the equation for the waveform every 60 degrees. The equation for the output every 60 degrees is the equation for the line voltage every 60 degrees. You can do that. Or, of course, it doesn't make sense to do that. You just integrate over one slot, 160 degrees, and multiply that by 6, basically. Or basically, you integrate over the period, 1 over the period of the periodic waveform, and you divide over the period of the periodic waveform and integrate over the period of the periodic waveform, which in this case was 60 degrees. So everybody's okay with where we got the 60 degrees from? And then they just, okay, this is integration of one of these waveforms, which is the Vmax line-to-line. Again, it's the line-to-line voltage, it's not the phase voltage, right? Anytime we're looking at the output here on this load, it's the line-to-line, right? It's the voltage between any of these two lines, A, B, A, or C. That's why it's line-to-line, and then sine omega t. So that when they did the integration, the value of the average output voltage was 3 Vmax line-to-line over pi, and then cosine alpha. And this alpha, I can make all the way from 0 to 180 degrees, right? So if I make it beyond 90 degrees, what do I get? I get the average output voltage being negative, right? So like the single phase full bridge. Remember the single phase full bridge? We changed alpha all the way until we got negative output. When we got negative output, we called it what mode? Inverter mode, right? One was rectifier mode, taking from AC to DC. That's called rectifier mode of operation. And then when we changed the alpha to greater than 90 degrees, meaning we flipped the output voltage, we called it inverter mode. Just a terminology, right? There's nothing changed about the circuit. And the only thing that changes is that I flipped the value of average output voltage. If I flip the value of average output voltage, while current is the same, what did I do to the value of average power? Current is in the same direction, because I cannot change the direction of the current, right? Current is always going to come out of these diodes into the load, right? I have no control over that. This comes with the structure of the circuit, right? So the current will continue to go in this direction, but the voltage polarity has been flipped on the output. That means that I flipped the direction of power flow. Power is V average times I average. Average voltage times average current. Average current does not change. Average voltage flipped its polarity. So the average power has flipped its polarity. So instead of the load taking power from the source, in this case, the load is sending power back to the source. And again, this is only possible if what? Alpha is greater than 90, but if I put a passive load, will this happen? If I put a passive load here, it cannot happen. If I put a passive load, if I put an RL load, RC, whatever, some impedance, if I put an impedance, a passive load, how does the impedance, a passive load, or linear load respond? A linear load responds, either it's going to look like a capacitor. A linear load is what? It's either a combination of RL or RC. That's the equivalent, right? Anything is going to be looking like an RL or RC. An RL or RC, if you put some waveform of voltage across it, what's going to happen? It will respond by drawing current. And this current will either be lagging or leading that current waveform depending on the value of the impedance that you have, right? So, but it's not going to be opposite in polarity, right? So if your load is drawing a positive current, if you're applying a positive voltage, then the load, if you have an RL load, for example, the voltage, for example, will what? The inductor in steady state will be a short circuit, for example, and then you will draw positive current, right? If you're applying a positive voltage across it, so eventually it will draw positive current, right? You cannot have voltage and current polarity being different in steady state for a passive load, correct? So the idea of flipping here only applies to the what we discussed last time about the PV panel, for example. If I have an active load, meaning I have a source, right? In this case, if I have a source configured in this fashion, then current can come out of here. The output voltage can be negative, no problem, right? Because and this source is allowing something like that to happen. I mean, it's in series with that output voltage that we have, and it's the current direction does not change, right? So we drew the equivalent circuit of this last time. Yeah, I think here we drew the equivalent circuit of that around this discussion last time, right? So if I make my output voltage negative, I need to put a source in a certain polarity in order to be able to transfer power from one side to the other. So in this case, I made my output voltage negative. This is a source. Current is going into the positive terminal, not out of the positive terminal. That means this source is being charged, right? Current cannot change its polarity because the thyristors or SCRs or diodes or whatever you want to call them on this side are facing up, right? So I put my PV panel facing down, and I can make this happen. I can move power from my PV panel. So this is a source, current coming out of the positive terminal of the source, meaning the source is providing power, right? So if this is a PV panel, then I can provide power from the PV panel, pump it back into the grid. That's a simple example of a load being added to this three-phase rectifier. Another application of that is connecting two different countries, for example, or two different countries, or two different regions in the same country, or different continents that have even different frequencies. Remember, to share power or for your generator to come online into the power system, to transmit power to the power system, you first need to synchronize the generator. If you did not take 338, I mean, think of it as two people running together, right? If two people running together and they're both holding, a heavy weight, lifting a heavy weight, if they run together, they can make it move, right? And sometimes one will lead the other, sometimes the other will lead. So that doesn't matter. As long as you're within a certain limit of angle difference between them, then everything will be fine. That's how the generators function, right? In two different countries, or if you want to connect to the power from two different countries, or have them both contribute to power transfer, if this country needs power at that certain time of day, while this country has excess, you should be able to pump power from this country to that country, or this region of that country to that region of the country. So one way to do it is a configuration that's called HVDC, high voltage DC back-to-back connection, back-to-back. Of course, you don't use it number two. A back-to-back connection. Back-to-back meaning there are two converters back-to-back, and one is pumping current, one is taking power from one source, sending to the other, one is taking power from, accepting power from the other source. It's called a back-to-back connection. So sometimes they're just when you have two converters right there next to each other in this type of configuration, it's called a back-to-back connection. And of course, it's done at very high voltages because we're transferring a huge amount of power, right? So if you're transferring a huge amount of power, you would like to raise the voltage as much as possible so that you don't have power losses, I squared R losses in your system, right? So this is another application of this three-phase controlled rectifier. And this is nice because this can be 50 hertz, this can be 60 hertz. This can be one voltage, this can be another voltage, right? Does not really matter. They can be the same voltage, but and the same frequency, but they don't need to be synchronized, right? Because you're converting everything to DC anyway, right? So you're making it look like a DC circuit. So I don't care about frequency, I don't care about magnitude because I can control the magnitude, right? So with a passive load, again, with a passive load it won't work because what a passive load would do, if you try to put a negative voltage across a passive load, in steady state, what's going to happen? You're going to have negative current. Put a negative voltage across the resistor, you will have a negative current. So the passive load would try to push current back into the converter, right? So if it tries to push the current back into the converter again, then these thyristors will turn off, right? All the thyristors will turn off if you try to push current back. So in inverter mode, you have to make sure that you have the proper load. When you operate in inverter mode, you're doing this because you want to transfer power from one source to the other, from the load side or the output side. So what this does is, again, this is the Fourier series. So instead, because these waveforms are periodic, but it's very difficult for us to come up with Fourier series at every value of alpha, for example, right? We can come up with an expression. And again, I'm not going to ask you to do that, right? So the nice way to do it is provided by the textbook. So one way to do it mathematically, what they're doing in this curve is taking this output voltage as a function of alpha and calculating the Fourier series, calculating the ANs and the BNs, and coming up with an expression for Fourier series. That's out of the scope of the course. So they've done this Fourier series graphically for you, right? So what this curve does is it calculates the Vn, the Fourier series voltage harmonics, voltage component, as a function of V maximum, which is your waveform's input maximum voltage, for varying degrees, for varying values of alpha, for the specific harmonics of interest. So why did they choose the 6th, 12th, and the 18th? It's because in the Fourier series you probably had the lower harmonics were probably cancelled in this type of waveform, right? If you go back to so now if I drag to if I tell you write the Fourier series expansion, for example, for this waveform at value of alpha of 40 degrees, so you go here, and you would see that the main harmonics are the 6th, the 12th, and the 18th. Why the 6th? Remember, an impulse function is a function that contains all harmonics, right? So now if I have how about the 50 hertz? If I have a pure sine 50 hertz, and I do a Fourier series, what do I see? What frequency content is there? Only the 50 hertz, right? How about if I have the full wave, three-phase full bridge rectifier for every cycle? What is the dominant thing that's happening? I'm getting 6 pulses, right? That's why you would see a multiple of 6 or a 6th harmonic being the dominant waveform, right? So you will see an average value for sure because it's DC, right? But from a harmonic content perspective, you need to understand what is going to be contained in your harmonic spectrum, right? Your harmonic spectrum will contain, you go to one full cycle, for example, of your fundamental and see what's happening. Something is happening 6 times, so obviously I would have a 6 harmonic. Something is happening 3 times, so like for example, for the half-wave rectifier, 3-phase half-wave rectifier, we had 3 pulses at the output, right? So if you go look there, you will definitely see a 3rd harmonic, being the highest frequency content. For the full wave rectifier, our input was, let's say, 50 hertz, but the output was 2 humps, right? It was the rectified waveform, right? So the output will definitely contain 100 hertz, right? So every fundamental period, you will definitely see a content that's 100 hertz, right? So you just need to understand. I mean, the Fourier series or Fourier components or harmonic spectrum is something very physical, right? So you need to get a feeling. You have a feeling of what's happening in the spectrum. Fine. Whether you have the how many of the components you have or whatever, that's beyond. I mean, how many components are of interest? That's not something we care about. You have to go into do this mathematically. But when you go here and see, fine, I have the 6th, 12th, and 18th. It makes sense because the 6th is going to be a dominant harmonic, and its multiples will exist, right? Its multiples will definitely exist. Yeah. So you would go here, and at 40 degrees delay angle, you would see that you would have a Vn over a Vm of a certain value for the 12th harmonic and the 18th harmonic, and from there you can calculate the value of Vn, because you have Vm, right? So if you have Vn, which is the nth harmonic of voltage for this waveform, and I ask you to calculate the nth harmonic for current, or the THD for current, the current THD. Right? To calculate the current THD, you need the current harmonics. Right? So if having the voltage harmonics and then knowing the impedance, if you have a certain impedance and the output, right, you can calculate the current harmonics. From the current harmonic, you can go and calculate total harmonic distortion. Okay? I think we went through something similar before in a previous chapter, but here they do it graphically. It's a nice way. You don't need to do the Fourier series even. Yeah. So another application of the same circuit, this three-phase active rectifier, is called the 12-pulse rectifier. So before we had this 6-pulse rectifier, right? So why did we go to the 6-pulse rectifier? The progress was as we had this half-wave rectifier initially, right? And we said, oh, ripple is too much, right? Ripple is too much, and this will require a big capacitor to store all this energy. So we went with a full bridge, right? The output of the full bridge was like this. Still very high ripple, right? But the amount of energy storage that I need to maintain the voltage until I reach the output voltage, until the capacitors charge again, is small, right? So remember, capacitance was equal to delta Q over delta V. Delta Q is the amount of area of current, area under the curve of current, right? So this is all time that the capacitor has to provide current to the load. So this is a long period of time. So delta Q is large. Delta Q is large means C is large, right? For the same delta V here, because delta V here is equal to delta V here, right? It's peak to peak, right? The voltage, the maximum value is here, the minimum value is here. So this is the delta V here is equal to the delta V here. But here I need the capacitor has to carry a lot of charge to maintain that voltage. Here the capacitor has to carry a small amount of charge to maintain the voltage, right? So then we said, okay, so this is a smaller capacitor. Then we said, oh, three-phase gives me even nicer capacitor, smaller capacitor, because in the whole period I was seeing something. This was. I was seeing something like this, right? 1, 2, 3. I didn't draw it nicely. Anyway, you know what I'm talking about, right? 6. We were seeing 6 of these pulses, right? If I drew the three-phase properly, like I drew it before in the class. So we were seeing these 6 pulses, right? So now the peak-to-peak voltage, the delta V here was small, right? It was from this peak value until I think it was half, right? I don't remember the number, but the delta V was decreased considerably, and the amount of time or the charge that had to be put in the capacitor was also much smaller, because the time is less, the value is less, so capacitor is much less, right? So this is nice. This is very nice. So capacitor here is even less, but for very high voltages and for very high powers, even these harmonic again. What was happening here? Remember what was happening here? What was happening during this period? What was the supply current doing during these shaded areas? What was the supply current doing? Sure. Sorry, yeah. What was the supply doing right before that? Sorry, right before, or right after these shaded areas. Sorry, right here. So between here and here, sorry, or between the beginning and here. Yeah, charging the capacitor. So what was the supply current looking like? These pulses, right? This was my supply current. Contains lots of harmonic content, right? This harmonic content is not, or for the three-phase case, it looked like what? For the resistive load, even it would look like, right? Lots of harmonic content. So anything that can reduce the harmonic content is great, right? This is even resistive load. I did not even put a capacitor yet, so the book doesn't even cover that topic yet. So, but for the single-phase case with a capacitive output filter, huge current spikes, lots of harmonic content. Something like that at very high powers. We're talking about megawatts, megawatt machines, right? A machine is like 50 megawatt machine at, I don't know, 50 kilovolts or 20 kilovolts. A machine like that, even a small amount of power that is being dissipated, these harmonics, can be harmful. And again, mechanically, these harmonics can resonate at certain frequencies of, for example, the shaft's rotation, and they will cause big disasters. I mean, it's if you have these harmonics available, and for example, the resonant frequency of your mechanical system was exact or very similar to this harmonic content, the harmonics can sort of supply or resonate or activate this resonance mode in the mechanical system, and the shafts can break, and you have big issues. Yeah. So sometimes you would need to you typically would need to filter these. You're not going to allow these to circulate in your system because they're going to also destroy the voltage profile, right? I mean, if you have currents that looks like this on your flowing through your cables, then the voltage drop on the cable, if the cable is basically a resistor, then the voltage drop is also going to look the same, right? So this voltage drop will be added to the voltage that is present on the cable that you're sending, for example. So it will ruin the voltage profile, right? So it will distort the voltage. It will cause additional power losses that you don't need in the system. So what people do is filter them, right? On the very high voltage side, if you would like to use these rectifiers, which are simple and you need them because you want to transfer this AC power to DC power, you would like to be able to reduce the ripple even further. So in three-phase, we said the ripple was reduced considerably, and we have in every pi, I have these 6 pulses at the output. 1, 2, 3, 4, 5, 6, right? So this was my three-phase uncontrolled rectifier output voltage for one period, right? So what if I do this? What if I'm able to use 2 of these in series? 2 of these bridges in series, 2 of these diode rectifier bridges in series, right? If I'm able to use them in series, and they're identical to each other, am I going to benefit anything from what will this times 2 equal or look like? The same, just increase in magnitude, right? But what if I don't just multiply by 2? What if I put them in series? Yes, but I make the second one same circuit, but I phase shift the waveforms somehow. So the 6 pulses, they will be 6 pulses. 1, 2, 3, 4, 5, and then this is the 6th one, beginning and end. Right? If I do that, what happens to my ripple content? Not zero. I mean, again, reduced even further. I mean, how much is? We have to look at the intersection of these 2 waveforms together exactly, and we'll see. But there is some ripple content. For sure, there will be some ripple content. But it has even decreased further, right? So how would you achieve something like that? Input. I would have to shift the input, right? How do I shift the input? I can use transformers to shift the inputs. Remember, we were looking at the phase voltage and line voltage issues. So we said that the line voltage. This is phase voltage A, B, and C. Then line voltage VAB, VA minus VB will look like this. This is VAB. So it leads by 30 degrees, correct? So how did this come about? It came about from the transformer's construction. Because I spatially have three windings. I actually have physically three physical windings in the transformer that are spatially phase shifted. So if you apply a voltage to them, or how does this happen? In the generator itself, if you study if you study the 338 course, you have a machine here. And this machine, for example, would have phase A winding here. This is phase A and its return. Phase B and its return. Phase C and its return. Right? So these are spatially, they are spatially distributed. They are spatially distributed, and there is physical space between them in the machine itself. So if you have a magnet here, north, south, and you spin that magnet, it will first cut A, then cut B, then cut C. And hence you'll be able to create voltages that are phase shifted with respect to each other. So this came from the generator side. The spatial distribution of the windings in the generator caused the 120-degree phase shift that you would see in three-phase systems, right? So similarly, transformers do the same thing. So here, the machine is easier to explain because the magnet here passes by each one separately. In transformers, I can do the same thing. If I have a star connected transformer, versus a delta connected transformer, I connect the windings like this, for example. Right, this is phase A, phase B, phase C, phase A. This is phase A here, B and C of my three-phase system. Right, this is the three-phase system that I have. What do I see here? I see here the line voltage. The line voltage is what? VAB, right? It's leading by 30 degrees and it's greater, right? So that's the line voltage on the star. It is also the phase voltage on the delta, right? So if I want to now compare the phase voltage of the star and the phase voltage of the delta, it's like comparing the line voltage on the star and the phase voltage of the star, right? The phase voltage on the delta is here, is in phase with the line voltage of the star. Right? So if I make a transformer, now I have this generator here, right? If I have this generator, I understand how to create three-phase waveforms here that are phase shifted from each other, right? I just spatially distribute the windings in the machine, simplistically speaking, right? So I have this generator, and then I go into a transformer. I represent this as the primary of the transformer, right? And then the secondary of the transformer, I have two secondaries. Again, I'm drawing this representing three-phase, okay? So I can draw three of those. But in power systems, we typically represent three-phase systems using a single line diagram or a single-phase representation. Why? Because of the condition. You remember last time when I said that, if you have a star here and you have a three-phase source here and you have three-phase load here, that there's no current flowing in this winding, right? So this is like what? This is like these 2 points are connected. Since there's no current flowing, I connect them. Since no current is flowing, there's no voltage difference between the points, right? So I can connect this point. I can connect this point to this point here, meaning I can take phase A outside by itself and do the analysis that I need to do, right? And that's a single-phase equivalent circuit, which you did in 338 if you took the machines course. Dr. Haytham was using equivalent circuit, single-phase equivalent circuits all the time. Why? It's because of this property. It's because of the fact that you don't have current going back in a balanced system. Since no current is going back in the neutral wire or in this fourth cable, then these 2 points don't have a voltage difference. Then you can just connect them to each other. If you connect them to each other, then where is your loop for Kirchhoff voltage law purposes? It's this one, this loop up here. And it's independent because these 2 points are, one node. So I take this circuit out. So that's why the three-phase system can be represented as a single-phase equivalent circuit, right? So that's why I represent the transformer as, one winding here, okay? And this would be my primary winding. and I will say that this winding is star connected. This is a three-phase star connected winding. Right? On the secondary side, I have two three-phase windings. One of them will be star connected. Right? Meaning what? Meaning one of them will look, so this is my primary, and I will also have, so, and this is one of the secondaries, and this is my second secondary. The second secondary will be a star connected secondary. The star connected secondary, I will connect it to here, here, and here, for example, right? So, or this is a star connected load and delta connected load connected to a transformer. But again, for a transformer, there's no physical connection, right? So I should actually delete this. There's a magnetic coupling between the primaries and the secondaries, right? But if I do this, what do I get? I'm able to, the transformer has, remember, it has a primary that's a star connected primary, right? And if the secondary is star connected, then, and it's a one-to-one transformer, then if this is phase A, this is phase A, right? If this is phase B, for example, this is phase B. If this is phase C, this is phase C, right? If it's a one-to-one transformer, one-to-one star-connected transformer. Let me draw it nicely. Transformer here, transformer windings. Right, this is being fed from a three-phase generator or three-phase source. And this is a transformer, right? So this is a phase A, and if it's a one-to-one transformer, one-to-one, then this is, if this is phase A, this will be phase A. If this is phase B, this is phase B. If this is phase C, this will be phase C. You agree? Remember, a transformer looks like this, guys, right? Right? Windings on the same magnetic core will couple magnetically. If they couple magnetically, that means that the same flux linking this winding will link this winding. So if the number of turns are the same, then the voltage generated on the terminals of the windings will be the same, because it's equal to n d phi by dt. Right? So number of turns is the same, flux is the same, so the voltage on the both sides of the windings, or both sides of the transformer will be the same. So think of this and this to be on the same core. So physically we would do that. We would have to construct it that way. These would be this on the same core. These two windings would physically see the same flux. They would have to. B, same thing. These would be on the same core. Or C would be on the same core, right? So if I do that, then then I put A here, if I phase voltage A here, I will see phase voltage A here. B here, B here. C here, C here. Correct? So I will have this three-phase output, right? Now, this applies for any winding, right? So I can now take my delta. Let me see what I can do here. Now I can, add a secondary here to the transformer. I'll add another secondary to the transformer. You can have a transformer with one primary and as many secondaries as you want, right? Or as you can put as many primary windings, as many secondary windings as you want, right? As long as something is at the end of the day gonna push the flux in the core. As long as you push the flux in the core and the flux cuts the other windings, then you will have back EMF generated in the windings, right? So it does not matter how many windings you have. But now that I've connected the transformer in a certain other way, what did we say is the relationship between the phase voltage on the delta and the line voltage on the star? This is the phase voltage of a star. The line voltage of the star was 30 degrees ahead, right? And this line voltage of the star, remember, if I have a star connected to a delta here, the line voltage of the star is equal to the phase voltage of the delta, right? The line voltage of the star is equal to the phase voltage of the delta. That means that the phase voltage of the delta is 30 degrees ahead of the phase voltage of the star. right? Okay. So now if I take, so this is the phase voltage of my star, right? This is my phase voltage, phase A voltage of my star secondary side of the transformer. And this is my, let's say, phase A voltage of my delta connected secondary of the transformer. I choose the number of turns here such that the output voltages are equal in magnitude. Okay? I will choose number of turns. But what is the relationship between these two with respect from a phase shift perspective? This one is phase shifted with 30 degrees with respect to this one, right? Because this is the line voltage of my star. The line voltage of my star, this is my V line to line of my star. This line voltage of the star is 30 degrees ahead of the phase voltage of the star. But the line voltage of the star is in phase with the phase voltage of the delta. Okay? So the relationship now between the phase voltage of the delta and phase voltage of the star is that this will lead by 30 degrees this phase. So now if I take these phase voltages that are here, these top phase set of phase voltages VA, VB, and VC, connect them to a three-phase rectifier here. And then take these, connect them to a three-phase rectifier, right? And then put these two rectifiers in series. And the output voltages, these are output voltage will be 6 pulse. Output voltage of this will be a 6 pulse waveform, but they will be phase shifted by 30 degrees. So you get a lot less ripple. Does it make sense? Some sense at least. So that's why you see here star star and star delta. But magnitude you can play with depending on the number of turns, right? So you can make you adjust the turns. That in 459 we talk a lot about that, how to select number of turns for transformers and create funky phase shifts and stuff like that. There's a lot of stuff we talk about in 459 related to that. That's why I cannot go. I mean, I'm not going to spend 438 doing that, but I just want to illustrate the principle, right? That you have to do this phase shift, and this phase shift, for you to do it, you have to provide two isolated sources, right? The source is here. This is like a source, like a generating source that's separately. This is not physically connected to this. This one is not physically connected to this winding, right? They are isolated. They're magnetically coupled, but they're isolated. Because if you physically connect them somehow, then you will end up with what you guys were doing yesterday, right? You will have windings connected to each other. You will be shorting out some windings and stuff like. You will not be getting the two output voltages in series that you're expecting. You will be losing you will be certain times, for example, you will have the top one, for example, shorting the bottom winding and trying to cause short circuits all over. So you will not be able to achieve that unless you isolate the sources. That's why, in oscilloscopes, if you try to, some oscilloscope probes are isolated, and some oscilloscope probes are not isolated. So let's look at this. If you have this, and you're trying to measure, and this is a VDC, for example, right? And you're trying to measure here, and you're trying to measure the voltage across the switch 1 and voltage across switch 2. Okay, let's say you're trying to measure voltage across switch 1 and switch 2. And these two switches are operating in complementary fashion. So if this is on, this is off. This is off, this is on. Okay? So what does the waveform here look like with respect to this point? When this switch is on, what will this point equal? 0, right? So it's 0, and then VDC, 0, VDC, 0, VDC. Correct? Right? How about, what do you expect the voltage across this switch to look like? When this switch is on, this is 0, this is off, So the voltage here will be VDC, right? So this one will be VDC 0, VDC 0, complementary, right? VDC 0, VDC 0. That's what you'd expect, top and bottom, right? But you can only measure that if this probe, the red probe, is isolated from the blue probe, right? And some scopes don't provide isolated channels. Some of them use the ground connection is common. So if the ground connection is common, then this thing here is no longer here. This probe is actually here. So if this probe is here, are you actually measuring the voltage across this switch? You're not measuring the voltage across this switch. So when you put your other probe end here, you're measuring the DC voltage, right? You're no longer measuring the voltage across this switch, right? So even if you have the ground terminal here, if you put the ground terminal here, what have you done? If you've taken your ground, if you actually do it, if you take your ground terminal, try to put it here. For this probe, probe 1, you try to put the ground terminal here. Probe 2, you put the ground terminal here. What are you doing? You have a ground here, and you have a ground here now. You have shorted out this switch completely, right? So that's why isolated probes are more expensive, and you need them. And these guys, of course, it's like a few extra chips or a small transformer to isolate, but they charge you more. They tell you, wow, this scope has 4 isolated channels. And that's why, because to measure different places in the circuit properly, or if you want to measure the actual voltage at the different nodes, then you need differential probes, right? So, or isolated channels. That's what they call it. More. They call it isolated channels. Yeah. Anyway, so we spent a lot of time on this. Sorry. So everybody's okay with this? So it's called a 12 pulse rectifier. Okay, so we had the single pulse rectifier, which is the half wave, the 2 pulse rectifier, which is the full wave rectifier, 3 pulse rectifier, which is the 3-phase half wave rectifier, 6 pulse rectifier, which is the 3-phase full bridge rectifier, 12 pulse rectifier, which is 2 of these in series. Then you can continue. Add more of these in series and phase shift. Add more complex transformers. You can add transformers. With a transformer, you can create any phase shift you want. So the next practical one is the 18 pulse. The following practical one is 24. You will find industrial products with 18 pulse and 24 pulse rectifiers. And all of that is to do what? Reduce the amount of capacitance required and reduce the amount of harmonic current. Why does it reduce the amount of harmonic current at the supply? Because if you have less capacitance, that means you have less current from the supply needed to charge that capacitance in this spiky fashion. So that means you're able to reduce the amount of harmonic current content. Okay? You see the justification for this kind of stuff? Okay, and after all this, if you still have problems with harmonics, then you put it, we discussed this. Then you put what we call here, I think they have one slide on it here. You put a filter. So at the end of the day, here you would have a 6 pulse, 18 pulse, whatever, how many number of pulses. And then you still want to make sure that harmonic currents are not circulating in your supply, so you put filters for each certain harmonic that exists. So if this is a 6 pulse rectifier, we were seeing that the input would have 3rd, 5th, 7th, etc., etc. So then you would filter, your 5th, 7th, 9th, 5th, 7th, 11th, etc., etc. So you would definitely add some filtering at the input of the converter. So Qatar Steel, for example, if you go to Qatar Steel, they would have these huge passive filter banks. Huge passive filter banks. Because they have a lot of, Qatar Steel operates a steel melting system, right? So what they do is they have these 2 electrodes. They come in. So this is the plate where the steel is, or the metal that they want to melt is like grounded, for example, and they bring an electrode at high potential. They bring this electrode at high potential close by, and they cause a short circuit, and this short circuit energy is used to melt the steel, right? So what are they doing? They're causing a short circuit intentionally, right? Causing a short circuit intentionally is doing something similar to this capacitor charging, right? It's huge current for a short period of time, right? And then they bring the electrodes apart to control the temperature until they quench the arc. then they, so they keep this short circuit, open circuit, short circuit, open circuit. This is how they operate, right? So they are either drawing a lot of current or no current, a lot of current. So that's adding a lot of harmonic content to the supply. So of course the utility doesn't like that. So what they tell them is, okay, if you want to do this, you can do this, but you have to add your own filtering stages internal to you so that this harmonic content is coming from the filtering stages. It's not coming from my supply. I don't want my supply, I don't want it to be supplying this polluted harmonic power. Yeah. So we said that, if I have a supply here and I have a source here of significant harmonic current content, right? If I'm drawing current that looks like this here, right? How do I make, and this is now coming from the supply, right? We will see in chapter 6, we'll do a lot of work on that. If we add a capacitor here, then all of this, then I can make my supply current look like a nice smooth, in case of DC, for example, nice smooth DC. Then if this is nice smooth DC, then what this content will be this capacitor will be able to deliver all this additional harmonic current that's available. So basically speaking, so this is a current with AC plus DC content. This I want to make pure DC, so I have to put a capacitor here to be able to provide the AC component. And we will design capacitor. And again, in chapter 6, I think we will go through and design capacitor. We did some of that in the rectifier. We talked about capacitor design, but we'll do a lot of that, especially on this case of harmonic. We'll draw some waveforms here with harmonic content, and we'll see how to size the capacitor accordingly. Yeah. So you would have to do that. You would have to add your own filtering stages as an industry, as a factory, to be able to prevent the supply from having to provide this harmonic content. Yeah. Right? And we will do that in chapter 6 in detail. Yeah. So that's what this is. Why 5th and 7th? Because of the Fourier components of the supply current. They found, okay, when you do the Fourier analysis of the supply current, you will see that if you go back here this is the Fourier series of the output voltage. Fourier series of the supply current is probably somewhere before. No, they didn't include it. Yeah, here. So this is supply current. Supply current Fourier series had the 5th harmonic, 7th harmonic, 11th harmonic, 13th, etc., etc. Which are the most significant ones? Remember we said that the harmonic current is basically the voltage harmonic divided by the impedance at a specific frequency. The impedance at a certain frequency increases with frequency, right? And omega L, if you have an RL circuit, the impedance, because of the impedance of the inductance, for example, will increase with frequency. So impedance will increase as frequency increases. And voltage magnitude decreases because again, if you look at the Fourier series components, you will typically have a V maximum over N, for example. There's a divided by N here somewhere, right? In the Fourier series of the square wave, for example, I don't have it here, but if you go back to the Fourier series for the square wave, it will be, for example, I don't know, Vn over N, and then cosine omega t or something like that, right? So the voltage harmonic is decreasing as the frequency increases. The impedance is increasing as the frequency increases. So the current harmonic will definitely decrease as the frequency increases. So the most important harmonics are the lower order ones, the 5th and 7th, maybe 11th. The lower frequency ones are most important. The higher frequency ones, they will be filtered easily because they are already at high frequency, meaning that their value is already very small. So what they did here was they lumped all the high frequency components together, and for the low frequency harmonics, they have dedicated filters because there's a lot of energy that needs to be dissipated. That's the logic. Yeah. But theoretically speaking, you can do one big filter, right? But can you dissipate all this energy in one single filter in a given amount of space, etc., etc.? That's a design consideration. What else? So we covered that. So we talked about connecting, two different countries or two different parts of a country using what is called high voltage DC or DC power transmission, right? It's called high voltage DC or DC power transmission. In DC power transmission, there are two sort of examples of that. One example is the connection between, for example, like Qatar and Saudi Arabia. We have a converter station that has the Qatari converter and the Saudi converter all in one area, right? These are right next to each other, right? That's one example of DC transmission. You're transmitting power from this side to this side, but there's no transmission line in the middle, right? That's one. So that's an example where there's no transmission line in the middle. It's just a bus bar, right? They're all in the same area. But for example, if you have an offshore wind farm, or if you have a power station somewhere in China, I mean, Qatar is very small, so but in China, for example, you have a hydroelectric power station somewhere a few hundred kilometers away from the city. You want to transmit that power to the city, right? You can transmit it using AC power across AC transmission lines, or now because we have power electronics, we can convert that to DC at the hydroelectric station, at the source, right? And then increase the voltage, right? And then send the power in DC. And then at the receiving end or at the city, then take that DC power, convert it back to AC using the other converter, the other three-phase active rectifier. Okay, so instead of having the two in the same place, like the Saudi Arabia-Qatar connection, they would be in different places and they would have a transmission line between them. What's the benefit of using that versus using AC transmission? That's what this slide is about, right? So again, if the inductance of the transmission line has zero impedance to DC, right? So if when we look at power 459, for example, we will actually represent transmission lines as pure inductors, because that is the bulk of their impedance, right? They're very big. So since the cross section is very big, the resistance is very small. So the resistance is very small, so really what's happening is we're transmitting a huge amount of current through these lines, and they're exposed to air, so we can make them very big. We don't need to worry about that. We want to be able to cool them easily, etc., etc. So we have very large resistances, big cross sections, but huge amount of current flowing through. Huge amount of current flowing through, meaning lots of magnetic field around the cable, so that there's lots of equivalent inductance, right? So there is an inductance associated with the line. And that is the dominant sort of impedance component of the transmission line, right? That's what dominates the performance in AC power system, actually. So in DC power systems, that doesn't exist, right? Inductance for DC are short circuits. Something else, in AC power systems, we hang the cables on these transmission towers, right? When we hang them on transmission towers, we make sure that the distance is far enough, because these are very high voltage lines. So they are at a certain potential, and the ground is at another potential, right? So you have two plates basically at very different potentials with a dielectric between them. So what do I have? A big capacitance, right? So I have a capacitance. So the capacitive leakage currents can flow from my line down to the earth, and that's why you would hear you would hear discussions about effect of transmission lines on humans, and there was, if you Google search, for example, having a gas pipeline, the idea of having a gas pipeline next to a transmission tower and the effect of that, having a gate, fence, metal fence, for example, if you have a farm and you have a metal fence next to going along with the transmission tower, is this fence going to be charged or not? I mean, there's a lot of discussion on that, and you have to calculate that. You actually will calculate. You have to calculate that. In 459, we will calculate the capacitance value. And this capacitance will cause leakage currents to flow from the transmission line to the ground. It's there, it's an impedance, it exists, right? So what is capacitance in DC systems? How does it behave? Open circuit, right? So inductors are short circuits. Capacitors are open circuits. So it's really nice. So I've eliminated two of the problems that occur in AC power systems that way. This is something that we can do now because of the availability of power electronics. When GE and Westinghouse were arguing before about AC and DC transmission, they did not have power electronics, right? So who won? AC, pure. AC has to win, because I can step it up with the transformer, bring it down with the transformer, no problem. But I didn't have power electronics, right? Now, because of power electronics being available, you have to do the comparison. How much power loss how much would I lose sending power in DC? How much would I lose sending power in AC? Of course, in DC, I have to make sure I have a converter station on one side, converter station on the other side to convert from AC to DC, and then from DC to AC again. That's a big cost. But I only have 2 cables instead of 3. right? Which means I have a smaller tower, less copper for the cables. Then I also don't have issues with the voltage drops across the lines, the inductive voltage drops across the lines, because the transmission line is no longer inductance. It's a very small resistance, period. Right? So how do you control power flow? A lot easier than before. In power flow, if you have two nodes, for you to push current from this node to this node, I just change the voltage with respect to each other. In AC systems, it's not that. I have to make sure I control voltage and angle. Voltage magnitude and angle. So I have all these synchronization issues that I need to worry about. In DC, I don't. Right? So I can control flow a lot very differently. I can control power flow in both cases. Here, a lot easier than here. But here I need a converter station, 2 converter stations. Here I don't. Here I need 3 cables. Here I need 2. Here I don't care about inductance and capacitance. Here I do, right? So it's all of these things are things to consider, right? So for you to make a proper assessment, you need to have full details. Typically, what we found, what people have found developing HVDC systems is for longer power transmission. If you're transmitting power over hundreds of kilometers, DC is very good. Or if you're transmitting power subsea in areas like harsh environments, like subsea environments, etc., DC power is a good option. If you're transmitting power in a country like Qatar, where we have 80 kilometers maximum area, Qatar from east to west is 80 kilometers, right? From north to south, maybe about 200 kilometers. So if you have the power station somewhere in the middle or around the middle, close to Doha, you're not transmitting power anywhere more than 80, 50, maximum 80 kilometers, yeah. Right? So it does not make sense inside Qatar. And then you have to have these big converter stations, etc., etc. Does not make sense. But in China, in the US, in countries where they have, transmit large areas that they transmit power over, it makes a lot of sense. Yes.
So, if I'm not wrong, we had the AC/DC debates test last time, right?
Sure.
So which particular type of transmission did you prefer?
AC is, again, because at that time for you to send power through DC, you would have had to do what? If I want to send power from the utility to my house in DC, they would have had to send power at what? 100 volts, 150 volts for the equipment to work. I mean, I cannot receive power at home here at 100 kilovolts, right? That's not very unsafe. You cannot do that. So, but with AC systems, I can, right before the house, I can put a substation, transformer, step down. And then right after the generator, I can step up. So my losses will be minimized. So nice and easy. But in DC systems, I cannot do that. There's no way to step up or step down without power electronics. And they did not have power electronics at that time, right? So if power electronics existed at that time, maybe we would have had something completely different today. But that's why people today, they're looking at DC microgrids. If you search IEEE right now, people are doing research on what? DC microgrids. How to power DC buildings, DC, data centers, DC blah, 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 right? Why? Because all of our devices today, all our computers, everything has this front-end rectifier, right? To take from AC, because all the electronics is DC-based. Most of everything we run is DC, right? But, so we have to have these rectifiers everywhere. And they're in series with our devices, right? So they're cutting off, they're removing a chunk of the efficiency coming into the system. So yes, ideally we'd love to have DC, everything running on DC, but safety issues are a concern, right? I mean, I cannot transmit power on DC at low voltages. I will lose a lot of power, and then the transformer, having a transformer is a big consideration. I know I'm isolated. On the transformer, primary can be at 1,000 volts. Secondary can be at 10. I can touch the secondary. Fine, I'll get shocked, right? But can I touch the primary? I can't. If I touch the primary, I will die, right? It's a very different voltage level here. So that's the beauty of the transformers. The beauty of the AC system is the transformer, the inherent safety protection that you have in there. You do whatever you want to do on the secondary side. You cannot get electrocuted by, you will not be exposed to the high voltage on the primary side. Right? In DC, what voltage level do you use? Is 100 volts safe? No. DC breakers, AC circuit breakers are a different story, right? Actually, breakers, they actually disconnect. The disconnection happens at the zero crossing of the AC. So the breakers, whenever the zero crossing of the AC happens, that's when they try to break, because otherwise you have current flowing. This current flowing will, if you try to remove contacts, 2 contacts that have inductive current flowing, will cause arcs. So you're trying to minimize this arcing energy. So if you try to minimize the arc energy, you try to disconnect the contacts when you're close to the D0 crossing of the current. So there's a lot of DC. How do you do that? So now there's a lot of research on DC breakers, right? So there are lots of people are doing research on DC breakers. So it's an interesting area. I mean, power electronics has changed the platform completely. So people are looking at different things that can be done. They used to be done in a certain way, and how do we do them now? And can we do them better, right? So is it possible? There's certain applications, yes.
And you mentioned about high voltage DC transmission. You said two lines will be implanted, right?
Yes.
What's the reason for the two lines?
Well, positive and negative. DC, yeah, you have a battery, you have two terminals, right?
Or we can't use the virtual ground.
Okay, there's a way to do it. Show you. Not this slide. This slide we went through something like that. So something like this, okay? What they did here, or what they do here, for example, is they have this think of this. This is one converter group, and current was flowing from out of these converters into the line, down these converters, being exchanged with the grid, for example, and then back through this line, right? If I make a identical copy down here, then and I have the same. I'm controlling the converter such that I'm transmitting the same amount of power from the top group and the bottom group. Then the current flowing through this line, from the top group, current will flow in this direction. From the bottom group, current will flow in the opposite direction, right? And if they're equal, then the current in this line is 0. Then I can sort of, eliminate this line and have, ground connections here, and I can sort of reduce. I don't know. I mean, you would sort of reduce the amount of conductor required to transmit a certain amount of power that way. So I don't know if it answers your question.
Also, is for high DC voltage, I believe you need like really big wires, right? And that would increase.
I mean, no. Cross-section area depends on the current density, right? So it does not really matter. The only advantage between AC and DC is the skin effect issue, right? There's no skin effect. That's the other issue that's probably listed in these points that I didn't go through in detail. I mean, please read them, right? But one of the other issues would be skin effect. Skin effect in AC, what it does is pushes the current towards the outside of the conductor, right? So you're utilizing less of the cross-sectional area. So yes, in DC, you would actually, for the same amount of current that you want to push through, you can probably live with a smaller conductor area because you don't have issue of skin effect, right? So you're using the whole cross-sectional area to transmit the current, not part of it. Yeah, so that's a good point. Yeah. So, but again, in short distances, it doesn't really matter. It doesn't make so much sense because of the converter stations. They're expensive. This stuff is expensive. It's not cheap. So, long distances, bulk power, the best solution. Definitely the best solution. Areas where I have under the sea, for example, where three-phase equipment and three-phase switchgear would be very expensive. Having DC systems would make sense, right? So, but classical open air power transmission applications in a short distance, no, does not make sense. Okay, the last thing in this chapter is the commutation effect in full bridge rectifiers. It's the same as the half wave rectifier commutation issue that we discussed. So, short and simple. Okay. Remember, typically we have current going through D1 and D2, and then through D3 and D4, correct? So we are passing current from D1 and 3, and then 3 to 1, 1 and 3, 3 to 1, and so on, and the same thing with 2 and 4, right? So current is being commutated between D1 and D3, and then 3 and then 1, 1 and then 3. So if 1 and 3 are on at the same time, what happens? What do I do to the source current? Because I have the inductance, and 1 and 3 are on, I have a short circuit, right? So look at this here. Source, inductance, diode 1 is on, and diode 3 is on, right? Both of these diodes are on. If both of them are on somehow, then we have a short circuit across my supply, right? Again, this is a condition. If I have a short circuit across my supply, I have a short circuit here, right? Then can I define the current flowing in the inductor or not? I'm putting the voltage source across the inductor. So if I want to calculate the current in the inductor, I would integrate the voltage across it. And that's what they did here. They integrated the voltage across the inductor, which is the source voltage, plus some initial condition. Right? So they integrated the voltage across the inductor. This is the supply current, right? So you have now an equation for supply current. What does for a full bridge rectifier, single phase, what did we say the supply current looks like for a resistive load? For the resistive load case, what did we say the supply current looked like? Remember, current is flowing through here, through diode 1 in the first half cycle, going to the load, coming back through diode 2. And in the second half cycle, I am flipping the polarity of the supply, right? So current flows through here, out this diode, through the load, back through diode 4, back to my supply, correct? So my output voltage looks like this, and my output current for the resistive case also looks the same. So if my output current looks the same, then what does my supply current look like? This is, remember, so how do you do the supply current? Kirchhoff current law at this node, right? So I need to look at diode 1 current and diode 4 current. This is what? Output current in the case of diode 1 and diode 2 on. And this is the supply or output current for the case of diode 3 and 4 on. So I have diodes 1 and 4 currents, right? So if I do Kirchhoff current law at this node, I can find supply current. Supply current in this case will look like a nice sine wave, correct? How about for the highly inductive load? For the highly inductive load, we said that we're not going to go through like RL case, blah, 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 but for the highly inductive load, the current will look like this. Supply current will look like this. We went through that when we were describing this. So I know the value of the supply current here, and I know the value of the supply current here because I said for the highly inductive load, it's like having a current source here with a certain value of I output. Right? So it's a fixed current. Highly inductive means the current does not change. So I can resemble this as a current source. So it's I output, for example, some I output current here. So that's what they rely on here. So this is the equation for current, okay, supply current in general. But at a point pi plus u is a point somewhere here, right? So this is my supply current, assuming there was no commutation. This was the square wave that we drew before, right? This was the square wave we drew before, and these were the sine waves or the rectangular waves in the diodes, diode D1 and D3. Right? So I know the value of the output current after the commutation process is complete, right? Because it's equal to what? It's equal to this I output current, right? So I know the value of output current or the supply current after the commutation process is complete. So, and that's what they were saying here. That's at a point pi plus u, after which the commutation process ends, my output current is equal to minus I output. So they take this equation for current and they equate it to minus I output, and they calculate for u, right? It's an expression in terms of u, and they calculate the value of u. Again, you don't need to go through the derivation. You just need to understand where it came from, and then you can use whatever you have in your equation sheet. But that's at the end of this process, you're able to calculate u. This u is the angle or the time at which the commutation process ends, right? So pi after for a time pi or an angle a time u after the value of pi here, the commutation process ends. So how will this affect the output voltage? If these two are on shorting the source, what's happening? What is the output voltage equal to in this case? right? So what was happening here? D1 was off, and now it's turning on. So D1 was on. If D1 is on, that means D2 is on as well, right? So D2 is on as well. So D1 and D2 are on here. We agree? And then what's happening here? D1 is turning off, but there's still current, so it's still on. Current's still flowing through D1, meaning it's still flowing through D2 as well. So, and now what's happening? D3 is turning on as well, because it's during this commutation process. So what's happening across my output? These two diodes are on now. I have a top diode and a bottom diode on at the same time, so my output voltage is 0. Right, so it's a time where my output voltage will be 0. Same thing as the single phase rectifier case, half-wave rectifier case before. There will be a time when the output voltage is equal to 0. And that's the commutation process here. So what does the commutation process do? It reduces your controllability region of your output voltage. So the equation for average output voltage changes because of the commutation process. Okay? Does this physically happen? Yes. If you have, again, anytime you have a cable, that means you have an inductance. So between your source, the generator, and your load, there's always an equivalent value of inductance. So you have to take it into account. How big it is will depend on the utilities, your power system itself. Yeah. But this is an extreme case, of course. There's no such thing as infinite inductance on the output, and there's no such thing as very huge inductance at the input. It's a very extreme case, right? But they're just introducing to the commutation process. So if you see notches in the output voltage, you don't see these nice, beautiful, rectified waves. Why is that? It's because of the commutation process. You have some source inductance, or yes, you have some source inductance, or the switches that you've chosen are very slow, the diodes are very slow. Something of that sort is happening here. Okay? So that covers the chapter. I think I explained, this is just nothing but the Fourier series. It's just a graphical way to do Fourier series. In your homework, you will do several of those. So you should be able to comprehend what I tried to describe at least. Again, we didn't go through and calculate the average output voltages, but it's an integration of the sine waves. You have to make sure you understand the limits of the integration and why they integrated over 60 degrees, not the 2 pi, and I think we went through that. What else? We talked about this. Again, you will not be asked to do a Fourier series, but if you're given a Fourier series of a square wave, for example, in this fashion, and you're asked to calculate THD for this current, you should be able to do that. This is the Fourier expansion for the current up to, I don't know, 5 harmonic terms. So you should be able to do something like that. Again, the waveforms, of course, I will not talk about that. You have to know the waveforms. Here we discussed the idea or the fact that the output voltage in a full wave rectifier, 3-phase full wave rectifier, will have multiples of 6 harmonic. It's an average value, and then what is the most dominant thing after that? You have these 6 pulses in the period. So definitely your most important harmonic content will be the 6 and its multiples, in addition to the average value. So if you do the Fourier series for that waveform, and we don't need to do it, but you will have the derivation in the text, this is something you need to understand. The physical relationship between the waveform shape and the harmonic spectrum. That's something that's there. They just describe that in more detail. They talk about, again, they derive the average value of voltage equation. So any questions on this chapter? So I think we spent a good amount of time on the chapter. We went through the R case, RL case, RL with the source case. The current waveform is the same in all. If you look at the current waveform for this case, for the RL case, the waveform equation for our current in this case is exactly the same as the half-wave rectifier, because that will not change, right? I have an inception angle and extinction angle. So the shape of the waveform will still have a forced response, a natural response. The forced response is here, right? It's the source voltage divided by the impedance. And they took the impedance as a magnitude only, and they brought its angle up here as well. Same as before. And then the rest of the component, the rest of the response is due to the natural response, and it's AE to the minus T over tau. A here is a sine alpha minus theta, blah, blah, blah. right? So these are equations you can have. I mean, you have in your sheet and you should be able to use. Yeah. But you just need to understand where where these equations came from. Yeah. So is everybody okay with that? Anytime we're not able to find the inception and extinction angle for the current means that I cannot find the equation for current easily, right? So in that case, what did we do? We had to resort to Fourier series, right? For the RL case, full bridge rectifier case, the current was continuous. In this case, I was not able to, I don't have an inception angle, I don't have an extinction angle, so there's no known quantities or starting for initial conditions for current that I can use to calculate the exponential equation, right? So in the exponential equation, ae to the minus t over tau, I was using my, for example, I at t equals 0, or I at alpha is equal to 0. And I was using that to solve for a, right? But in this case, I don't have that. So in this case, what does the book always resort to? The Fourier series of the voltage. Because the voltage waveform is something you know. It's a sine wave. It's always, the voltage, output voltage waveform is always going to be the equation of a sine wave. It's just that the terms of the equation will differ. I mean, here I'm from alpha to pi plus alpha. That's the the output voltage is integrated along this, and then the Fourier series is derived along from there from these based on these terms as well, right? So anytime you don't have a nice simple equation for current, this inception angle, extinction angle means that you cannot use the equation for current that we used before, and you would have to resort to the Fourier series of the voltage, and then based on the value of the impedance, you calculate the current harmonics. Now, if you have the voltage harmonics and the current harmonics, you should be able to calculate voltage THD, current THD, power, right? Input power. Input power, if in the case of the input being a sine wave, will only be the fundamental voltage and the fundamental current, right? Everything else, all the rest of the current harmonics will just be dissipating power in the system, right? But the average power transmitted to the load can be calculated from your fundamental voltage and fundamental current, because my voltage input is a sine wave. Since my voltage input is a sine wave, then only the fundamental current can cause average power transfer to the load. The rest of the current components are just losses. Okay, so that's something that, if I ask you to calculate the average power transfer to the load, and for example, your voltage at the input, and you were given, for example, the Fourier series for your current, you should be able to use that to calculate the average power from the input. You should be able to use that to calculate the input current THD, etc., etc. Okay. So any questions on the waveforms or circuits? Yeah.
Do we have any restrictions for the formula sheet?
You have to use the formula sheet I gave you.
Oh.
You have to use the formula sheet I gave you. I will put up a previous exam with solutions, probably today. Okay, I'll try to put 2, but if I don't, I put at least 1 exam with solutions. Yeah.